So what does it mean? It basically a kind of function mapping from one group to another. Say this is one group, say G1 with respect to say star. So this is G1, and say another group G2 with respect to say dot. Then a homomorphism is nothing but a mapping from this group to this group, which preserves the algebraic structure. What does it mean? If we have say AB here, then A star B will be an element here. So if I apply F over A, then that will be FA, similarly FB, similarly F A star B, also FA composition FB. That will also be an element of this G2. But if it happens to be the case that if A star B is always FA composition FB for all AB belongs to G1, then we called this F, the mapping from G1 to G2, a group homomorphism. For example, in our last class, we have already described about, for example, say, this is my Z, and say this is a smaller group, say Z2. So you can understand that it has two different kinds of elements, mostly even and odd. So this is a group with respect to addition, and this is a group also with respect to addition modulo 2. So if you have seen that the algebraic structure like even plus even, it gives me even plus odd, it gives me odd plus even, it gives me even, and odd plus odd, it also give me, so it should be odd, sorry, odd, and odd plus odd is even. So suppose, so this is algebraic structure followed by this plus sign. Okay. Now suppose I want to define a mapping f like this. F of any even number should map to class 0, and f of odd number should map to class 1. Then you will see that the similar kind of things are happening. 0 plus 0, their classes equal to 0. 1 plus, say 0 plus 1 equal to 1, 1 plus 0 equal to 1, and 1 plus 1, it gives me 0. The same thing. So if this is even, this is also even. So this is even, this is odd, this is odd, this is even, and both of them are odd. So here we have both of them are odd, but they will give me the even. So this kind of algebraic structures are preserved by this the function f, and then we call this as a homomorphism from G1 to G2. So when we talk about homomorphism, a natural term, few natural terms came into picture. For example, kernel of f. So what is kernel of f? This is all such element x belongs to G1 such that f of x equal to the identity element of the other group. That means all such element which maps to the identity element of this group. So the collection of all such elements are called the kernel of f. Similarly, we can define image of f, that means all such elements which has the pre-image. So as you understand that image of f is a subset of G2. So we have proved in our last class that both of them, they are subgroups. For example, kernel f is a subgroup of G1 and image f is a subgroup of G2. Okay. Also, we have seen few interesting properties like f of E1, where it should go. Anybody can tell me f of E1, where it should go if it is a homomorphism?
E2.
E2. Very good. Similarly, f of say A inverse equal to f of A whole inverse. So here the inverse is on A, but here the inverse is on FA. Similarly, if you have some elements, say order of A equal to n, and say this order of, can you tell me what should be the order of FA? So order of fa. Any information about order of fa? If order of a equal to n, then what should be? What can you tell about order of fa? Anything? Anybody?
Divisor of n.
Okay, so you say that n divides order of fa. Everybody agrees with him?
No, sir. Order of f divides n, sir.
Okay, other way around. So he says that order of fa divides n. Okay, so everybody agrees with this?
Yes, sir.
Okay, so he says that order of. How will you prove it? Any idea how will you prove this? Anybody? Any proof?
Whereas a order of a is equal to n, then a to the power n is equal to identity. Then
Okay,
if I apply
as order of a equal to n, a to the power n equal to identity this. Very good.
then if I apply the f both the sides,
This equal to f of e1. That implies
and then
f
f
of
of
a
whole to the
whole
power
to
n
the
is
power
equal to
n
e2.
to e2. Very good.
Then
Then
should order of fa must divides n.
yes. Then we have already seen in that case order of fa. So order of fa is the least positive integer such that fa to the power that order, say k, if this is equal to k, then k is the least positive integer. Least positive integer k such that fa to the power k equal to identity of 2. And in our last class, we have already seen this property that if this is equal to E2 and if something to the power n is also E2, then this is, since this is the smallest positive integer such that this happens, k must divide n. Okay, so that is order of fa must divide n. So we have proved this result. Very simple result. Okay. But these results are very useful with respect to many problems. Okay, so let us try to have some homomorphism first. Okay, for example, let us try to find some homomorphism. So find all homomorphism from, say, Z6 plus to Z4 plus. Let us try to see. Okay. Okay, can anybody tell me how many homomorphisms are there? Anybody? Any idea? Okay. So in my problem set, you will find a more general result, and in many competitive exam, this result is very useful. So
Two.
yes, two. It says that the number of group homomorphisms from Zn to Zm is, do you know? This is
GCD of MN.
GCD of n and m. Okay, so this is very useful result. In my problem set, you will find this problem, but for the time being, I am not doing that problem because that's already in my problem set. You need to do that. Instead, what I'm saying that for a particular case, try to find the idea how similar kind of results can be derived. Okay. Okay, so solution, let us consider, let phi from Z6 to Z4 be a homomorphism. Okay. Now, this is a cyclic group and it is also going to a cyclic group. right? This homomorphism from a cyclic group to a cyclic group. So if you have a cyclic group, or if you have some kind of basis or some kind of generator set, then it is very easy to find all possible homomorphisms. So you can write it phi of, say, any class A. So this is nothing but phi of 1 plus, I am just writing A means class 1 plus class 1 A times. And since this is a homomorphism, see, both the cases I am using the same class. Now you are matured enough to distinguish both the classes are not the same. So this class, okay, so let me write it in detail maybe. So if I write it, then this equal to phi of class 1 plus class 1 plus class 1. How many times? A times, right? A times. Okay. But if this is say minus 3, then you cannot write minus 3 times. Then minus 1 plus minus 1 plus minus 1 3 times. Okay. So that is, I mean, already given. Or you can always write, say, for example, in class minus 3 is equivalent to how much in Z6? Quickly. Class minus 3 is how much in Z3? I already gave you one idea how to do so. Minus 3 is how much in Z6? Same as how much class of how much? I want to represent it in a positive way.
Three. Three.
Simply just add this 6, whatever it may be, just add that in to this to make it positive. So if you add 6, that becomes 3. Okay. So in that way, you can understand that even if this is negative, you can always convert into a positive representation. If it is 0, then it's fine, then 0 times. Otherwise, you can always write in a positive term, and then you can add a many times. And this plus is not same as, by homomorphism property, you can write it like this: phi of class 1, phi of class 1, how many times? A times. And you are now matured enough to understand that this plus and this plus, they are not the same. So this plus is from this plus, and this plus is on the right side. That means this plus. Okay. So this is nothing but A of phi of class 1. So you can understand that the whole function at any point, evaluating at any point, can very easily be done if you know what could be the value for phi of class 1. If you know what could be the value of phi of class 1, then just multiply with A. That will give you all the remaining elements. So to find the values of phi at any point, it is sufficient at any element, it is sufficient to find this value at 1. Right. So to find, that is to find the value of, the value of phi of class 1. So its value means phi's value. So that means if you are able to, by some means, if you are able to find the value of phi of 1, then you are done basically. Then you can find the value of phi A at any A. Okay. So the question is, what is phi of 1? Phi of class 1. So how do I now proceed? So what could be the value of phi of 1? Now you know that this phi of 1, this is an element of this group. So phi of 1 must divide the order of the group by Lagrange's theorem. So this, the order of this element phi of 1 must divide the order of the group. Also, just now we have already seen this property, that order of fa must divide the order of A, right? So what was the order of A? So A is my this element. So what is order of A? Is 6. So order of phi 1 must divide 4 as well as 6. Is this step clear to all of you? Why this is 4? Because phi of 1 is an element of Z4. So this is an element of Z4. So this order by Lagrange's theorem, order of this must divide the order of the group. So it's 4. Now why 6? Because just now we have seen that order of phi 1 must divide order of class 1. And what is the order of class 1? Class 1 is in Z6. That means, so order of phi of 1 must divide 6. Then what could be the order of phi of 1? Tell me what could be the order of phi
Two.
of 1? Sorry?
Two.
Only 2.
So one and
One or
two.
two.
Yes. Then order of phi of class 1 is either 1 or 2. So it divides both. So if its order is 1, then also it divides both. If its order is 2, then also it divides both. So this 2 comes from the fact that this is nothing but the GCD of 4 and 6. So this kind of information will be useful in proving your general result. Okay. Okay. So now if order of phi of 1 equal to 1, then what can you say about then what is phi of 1? Which element has order 1 in Z4? So phi is a mapping from Z6 to Z4. Which element has order 1?
The class 0.
Identity.
Yes. So exactly there exists exactly one element from any group. So if G is a group, there exists only one element because identity element is the unique element. Only element E whose order is 1. No other element has order 1 since E is the unique element there. So since this is 1, it must be 0 element. Then what is this? Then this should be equal to class 0 because just now we have defined this is A into class of. So if you write it in details, then this is same as class of 1, and just now we have seen that class of 1 equal to 0. So this is 0 for all class A belongs to Z6. So what kind of homomorphism is this? Class A goes to class 0. What kind of
The
homomorphism?
trivial homomorphism.
Trivial homomorphism. So this is the 0 homomorphism. Now if order of phi of class 1 is 2, then what can you say about what should be then phi of class of 1? What should be this value? So in Z4, how many elements are there of order 2?
The
Two.
only class
Two.
2. Two. Only two.
Only 2. So in Z4, only class 2 is there whose order is 2, no other element. Remaining elements are order 4. One is 1 and the remaining 2 are there of order 4 and only one element is there of order 2. So this should be class of 2. That implies phi of class of A equal to A of 2 into 2. That means 2A. For all A, for all class A belongs to Z6. What does it mean? That means this is a function. Now you need to check whether this is a homomorphism or not. Now phi of class A plus class B equal to phi of class A plus B equal to 2 of class A plus class B. Sorry, it should be together. be 2 of class A plus B, and that is same as 2A plus 2B, and that is same as phi of class A plus phi of class B for all class AB belongs to Z6. That means phi is a homomorphism. Okay. So how many total homomorphisms are there? So we have exhausted all the properties. So how many homomorphism?
Two.
How many homomorphisms are there? Then 2. So we have exhausted all these properties, either 2 or 0. I mean 2 or 1. And in both cases, I have seen that there exist only 2 homomorphisms. So there exist exactly 2 homomorphisms from Z6 to Z4. Okay. Now quickly, can you be able to tell me how many homomorphisms are there from, is it clear to all of you? Is this clear to all of you? How this only 2 homomorphisms are there? Is it clear? Okay, good. Now quickly tell me how many homomorphisms and what are they? How many homomorphisms are there from Z4 to Z6? I have just reversed it. It was initially from Z4 to Z6, now Z6 to Z4. Okay, quickly give me the answer and give me. So here I have already shown you what are the homomorphisms. So you need to tell me what will be the homomorphisms. So one homomorphism was this and another homomorphism was this. Similarly, you have to tell me what would be the homomorphisms. Okay,
Say two homomorphism can
two
be possible.
homomorphisms, but tell me what are the homomorphisms. Homomorphisms. What are the homomorphisms?
So first is group trivial homomorphism,
Yes, so this is a trivial homomorphism, and then
and then
another one,
f of class A equals to class 3,
class 3A.
3A.
All class A belongs to Z4. So everybody got this? Good.
Yes.
Yes, sir.
Okay. Okay. So now today we'll discuss about another very important term that is known as isomorphism. So iso means same. So homo means similar, but iso means same. Okay. So formally it's very easy to define. So again we had two groups, G say star and say G2 dot, and F is an isomorphism if is a bijective homomorphism. Okay. So let us try to understand what do you mean. So first thing is that F should be a homomorphism, and then F should be a bijection. That means both injective as well as surjective. Okay. So let us try to write down few of the groups. Okay. Say Z4, say this I minus I plus 1 minus 1, and say uh, say what can I, okay, so maybe Z5 star. You remember what is Z5 star? That means U5, group of all units. That means all such class A belongs to Z5, such that GCD of A and 5 equal to 1. Okay. So we have seen that if say my G1 is Z4 with respect to addition, say G2 is my this with respect to dot of complex numbers, and say Z5 with respect to multiplication modulo 5, say this is my G3. Okay. So there are few groups, 3 groups are there. Now tell me few of the algebraic properties. First of all of them are groups. So they are group, group, group. They are finite group, finite, finite. Then is this group commutative? Is this group commutative?
Yes, sir.
Yes, sir.
Yes.
Commutative. Is this group commutative?
Yes.
Yes, sir.
This is commutative and this is also commutative because it's class A dot class B equal to class B dot class A. So this is also commutative. Okay, how many subgroups are there of Z4? How many subgroups? So number of subgroups of G1. How many? Anybody tell me how many? Similarly,
Sir, 3.
Sir, 3.
okay, who are they? E, then E means 0. I'm not writing say class, I'm dropping the notation of class. I'm just writing 0, class 2, and then G1 itself. So here, who are they? So number of, this is also 3. Who are they? 1, 1 and minus 1, and the whole group, G2. And who are they? Class 1, 1 and then who? 1 and so here how many subgroups are there? Tell me. So now you can understand who are there in Z5 star. Which elements are there? Z5 star means all the elements class 1, class 2, class
Sir,
3.
1 bar and 3 bar.
Okay, somebody says 1 bar and 3 bar. Let's check. If I multiply 3 by 3, then it will be 9. And modulo 9 is modulo 9 is class 3?
No, sir.
No, sir.
It's not. Then 3 is not a correct answer. Tell me which element?
Sir,
Sir,
1 or 4. 1 and 4.
1 and 4. Okay, let's check. If you multiply 4 by 4, this will be 6. Sorry, 16. And 16 means class 1. So class 1 is already there. So order of class 4 is class 2. I mean, order of class 4 is how much? With respect to multiplication, it's 2. Because 4 square is 16. That becomes 1 here. Right? Okay, good. So, and also Z5. Any other Z5 star? Any other subgroup? Can you think of this? No. Okay. Then is the group cyclic? Is this group cyclic?
Yes,
Z5,
sir.
Yes, sir.
cyclic. Is this group cyclic?
Yes, sir.
Yes, sir.
And is this group cyclic?
Yes, sir.
Why?
So 2 and 3 are generator.
Okay. So let's see. Here in Z5, who are the generators? In Z5, Z4, who are the generators? Class 1 and class
3.
3. Okay. Here in cyclic, here, who are the
I and
generators?
minus I.
I and minus.
Minus I. Very good. And who are the generators here? According to him, is class 2. What is the order of class 2? Can anybody tell me what is the order of class 2? So class 2 square is 4. It's not E. Class 2 cube is how much? 8. 8
Three.
cubes
4.
is 3. Yes. Class 2 to the power 4 is 16. That is 1. So
1.
order of class 2 is 4. So this is a generator. Any other generator?
Plus
3,
3.
3.
Class
Class
3.
3. Okay. So you see that they are different looking groups, but they have quite a similar properties. Now tell me one of the property which is not satisfied by some of them. That means one group satisfies one algebraic property, but the other group does not satisfy the same property. Okay, for example, let us increase the group. So maybe I just make a short here. I'll just put it here. Okay, so you understand what do you mean by Z5 star. Something is Z5 star. So that was my G3. And let's start talk about another group, say Z2 cross Z2, and maybe another group K4. So order of all the groups are 4. So they are group of order 4, order 4, order 4. So this is also a group of order 4. This is also a group of order 4. Finite. This is also finite. All of them are commutative. Number of subgroups. How many subgroups are there here? Z2 cross Z2. How many subgroups are there? So the elements are they look like class 0, comma, class 0, class 1, comma, class 1, class 0, comma, class 1, class 1. So the four elements are like this. Now tell me how many subgroups are there?
So only three.
Only
Two
3.
trivial subgroups. Two trivial subgroups, and one is 0 bar, comma 0 bar, and 1 bar, comma 1 bar.
So how many?
That's 3.
Total 3 subgroups. Okay. So you say that 0, 0 is one subgroup. I'm dropping the notation of class. Then, so if I write it like E, then will this be a subgroup? 0, 1, will this be a subgroup?
No, sir.
Okay,
Yes,
this,
sir.
what is the order of this element?
Yes, sir. Subgroup, sir. 2.
2.
If, as I mentioned in my last class, if you have any element whose order is 2, then you can just combine with E, that forms a subgroup. Because this is, if this is of order 2, then it will be the self inverse. So inverse of this is also within this, then E and so on. So this is a subgroup. Then tell me how many subgroups.
Sir, 5.
Okay,
Sir,
let's
5.
see. Then E 10 will also be a subgroup, right? Then who else? What is the order of this 1, 1? Then
2.
Two.
E11 is also a subgroup. And then if I call it G4, so G4. So you see that altogether it's 5. Okay. So first property that is deviates from the other groups is here. So all of them, they had 3 subgroups, but this is for the first time we have seen that this group is having order 5. Now tell me how many subgroups are there for K4?
5.
Yes, that is also 5. So you know that what is K4? E, A, B, C, and the subgroups are E, EA, EB, EC, and K4. That is my G5. Okay. So both this and this, they have a similar property. Now, none of them, are they cyclic? They cyclic
No,
group?
sir.
No, sir.
Not cyclic. Not cyclic. Again, they have the similar property. And these two properties are quite different from this group. But few properties are there which are satisfied by all. Okay, so that's quite interesting. So now you can think of, maybe I have already seen 5 groups of same order, but at least few properties are similar and few are not. So that actually gives the idea of, then you may think of that, why not any other group? Why not G6, G7, G8, G9, and so on? Infinitely many groups you might have think of. Then how will you characterize them? That's one of the very interesting and basic properties for group. Okay, how do you characterize them? Okay, first let us try to think in this way. Suppose I have a cyclic group, finite cyclic group. Very important theorem. It says that let G be a finite cyclic group of order n. Then G is isomorphic to, with whom? G is isomorphic to anybody?
Zn.
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 Good. Zn with respect to addition. Okay, that means what it says, that whatever be the group you take, if its order is n and if it is cyclic, then it must be isomorphic to Zn plus. Okay, if this result is true, then what you can say, that this is a cyclic group of order 4. This is a cyclic group of order 4. So all this cyclic group of order 4 must be isomorphic to Z4 plus. Can you now define a mapping which is an isomorphism? That means which is a homomorphism as well as bijection from Z4 to this or this to this. Okay, let's try to from here to there. Can anybody tell me? And then from here to here. Anybody? A mapping. So which element should go where? So here, so this is class 0, class 1, class 2, class 3. And here I have 1, minus 1, plus I, minus I.
So 1 goes to class 0.
Okay, 1 goes to class 0. This is the property of homomorphism, right? If it is a homomorphism, then identity element must go to the identity element. So this step is very easy. You have to do. If you do like 1 goes to class 1, then it will not be a homomorphism, because in homomorphism, 0 element must go to the 0 element. Okay, so this is the identity element here, and this is the identity element here. And then
The minus 1 goes to 2 bar.
minus 1 goes to 2 bar. Okay,
So plus iota goes to 1 and minus iota goes to 3.
plus I goes to 1 and minus I goes to class 3. See, since they are isomorphism, that means they will have a similar kind of, everything similar kind of pattern. So you can understand that what are the orders here. So this order is 1, this order is 4, this order is 2, and this order is 4. And if you look at what are the orders here, this order is 1, minus 1 order is 2, plus I order is 4, minus I order is 4. So 1 goes to 1, it is done. Then there exists only one element whose order is 2. So that must go to the order 2 elements. Then only the similarity will come. Similarly, the 4, there are 2 elements here. So if you, now my question is, he has given a nice ordering, nice correspondence. Now if you do like this, I goes to, he sent I goes to class 1. Now if you send I goes to class 3, will that also be a isomorphism? Is
Yes,
it
sir.
clear?
Yes, sir.
Yes,
Okay.
sir.
That will also be a important property. That means generator must go to a generator in case of an isomorphism. So you see that there are only two generators here, and here also we had two generators. So this generator must go to this generator, and this generator must also go to. But here we have two options. So for class I, it might be going to 1 or 3. If you send class plus I to 1 and minus I to 3, that will be an isomorphism. Similarly, if you send class I to class 3 and minus I to class 1, then also that will be a homomorphism. Now quickly tell me about U plus. So here we had Z 5 star, that is U5, and here we have Z4. So elements are class 1, class 2, class 3, class 4, and here elements are class 0, class 1, class 2, class 3. Now tell me where it should go.
So 1 goes to 0.
1 goes to 0, that's the first part. Identity must go to identity, and then
Sir, 2 goes to 1.
2 goes to 1. So you can see that the order of class 2 is how much? Here the
Sir,
order of
4.
class 2 was 4, right?
4.
So it must go to a generator, that is class 1. It can
Sir,
also go to class 3, does not matter. Similarly, class 3, the order of class 3 was how much?
4.
Order of class 3 was also 4. So you can also send this is to any of the generators, either this or this. And this is a unique choice. Class 4 goes to class 2. So if you define like this, then you will find that all the properties are same. You just renaming them. Then why should we study all the different groups separately? There is no need to find all the algebraic structures of all the different groups which are same essentially. Why should we study them? That's why for algebraists, this isomorphism is one of the most fundamental things. It actually gives you a kind of classification. That means all the three groups are essentially the same group Z4 plus. Then it is sufficient to study all the properties of Z4 plus. And if you just switch it to other groups by suitable mapping, then you will find exactly the same properties in that different groups. So that's why isomorphism is very, very important topic. It gives you basically the concepts of feelings of similar thing or exactly the identical things. Okay, so let us come to the proof of this result. Let G be a finite cyclic group of order n, then G is isomorphic to Zn plus. Okay, so let, since this is a cyclic group, G must be generated by some element. Okay, so G, say G dot is our group. So any element of G can be expressed as how? That means it will generate all the elements. What does it mean? It will generate like you start with A, then A composition A. So if I write A square, then A cube, then A to the power 4, and if I go A to the power n, then what should be the last element? A to the power n must be equal to
identity.
Identity.
identity element. So you see that a square, a cube, a4 up to a n minus 1, it will give all the elements of this. Okay. So let's have a look at how it is giving like this. So we have already seen this, but for example, in Z5, in Z5 star, let us try to understand how it is. So just now you have mentioned class 2 is a generator. Okay. So class 2 to the power 1 gives you class 2, class 2 to square gives you class 4, class 2 cube. What is class 2 cube? This is 8. This means class 3, right? 8 in Z5 is class 3. and then 2 to the power 4, that is 16. 16 in class 5 is class 1. So you get all the elements of, so class 1, 2, 3, 4, you get all the elements 1, 4, 3, sorry, 2, 4, 3, and 1. You get all the elements if you have class 2 as a starting point. So it has the ability to generate all the elements of the group. That's why this is a generator. Similarly, you can check that if you start with class 3, then it gives you class 3 to the power 1, class 3 square, this is 9. That means class 4. If you consider class 3 cube, this is 27, and 27 means class 2. And if you do 2081, that means class 1. So again, also you see that class 1, class 2, class 3, and class 4 are generated from class 3. That's why class 3 is again a generator of the same group. So it is generated by also class 3. Okay. That's why, so suppose A is my generator, so you can write all the elements in terms of a square, a cube, dot dot a to the power n, right? Okay. So now what you need to define, you need to define a mapping from, let us define a mapping. Let us define a mapping phi from, say, from the group, say G to Zn by. How shall I define a mapping? So you need to have some elements. Just now we have seen that any elements must look like this form. So where should I send it here? Any idea where should I send this a to the power I? Where should I send? So it should be some element of Zn. So which element do you think that it should be an mapping? Any guess?
Sir, I.
I is not an element of Zn. It should be a class. But you are almost right. So I is
Class
an
I.
integer. I is an integer, but you need to put some class here, Zn,
Class of I.
class of I. Very good. Let's see. For all a to the power I belongs to G. Okay. First, let us try to find how it is happening. Okay. Is the function, so what you need to prove? You need to prove three things. One, it's injective, then surjective, and then homomorphism. Okay. So if it is, how do you prove that this is injective? What is the idea to prove? Okay, so let phi of, let, okay, so directly you can prove like this. Suppose let a to the power I equal to b to the power I. Okay, so a to the power I equal to a to the power j. What you need to prove? Class A should be equal to class J, but that will give you the, not the injective property. But if I do it if and only if, then that will give me both injective property as well as the well-definedness property. So what you do in well-definedness, if x equal to y, it should give you phi x equal to phi y, right? And what is injective? One way of doing injective is that assume this, proof that they are equal, right? Okay. So let us try to have a look at what he is doing here. Suppose ai equal to aj. Okay. That is if and only if when they are equal, when they are equal, then you can write this equal to e. And when you say that if and only if this order is n and this to the power e, this to the power I minus j is equal to e, that means order must divide, sorry, what should I do, write this? So this is I minus j. Also we have a to the power n equal to e. Then what should I write here? What should I write? Tell me, what should I write? Can I write this n divides I minus j? Can I write like this? So
Yes, sir.
if and only if class I equal to class j equal to phi of ai equal to phi of aj. So this shows phi is well defined and injective. Note that injective is like this. If phi x equal to phi I, that should imply x equal to y. So since this is if and only if step, so this equal to this implies ultimately ai equal to aj. So in one way, in one run, we have defined that this is well defined as well as this is injective. Okay. So now this is surjective. Do you really require to prove that this is surjective? Any idea? So why
Because
do you want
both
to extract?
they G and Zn are finite of order, and they have both of order n.
Yes, very good. So we really do not require to prove that that is surjective. Surjectivity follows from the fact that this is already injective and both G and Zn, both of them, they are of order n. So that means they are of same order and injectivity is already there. So surjectivity will automatically follow. Now the only thing that it remains is we need to prove that this is a homomorphism defined in this way. So how will you define? So take ai into say a to the power j, that should be equal to phi of a to the power I plus j, and that is class I plus class j, and that is class I plus class j equal to phi of a to the power I plus phi of a to the power j. For all a to the power I, a to the power j belongs to G. Okay. So that is the proof. Very simple proof. That means if you are having, even if 3, 4, 5 doesn't matter, how many groups are there of same order, and if at least one of them is cyclic, then you don't need to find the different properties, algebraic properties separately. So it is sufficient to then consider only Z4 star if we Z4 plus if we consider G2 and G3. So you don't need to study individually each of the groups. That's why only studying only one group will give you the idea of many similar looking groups. So that is true only for finite cyclic group. Okay. Now, what's about infinite cyclic group? That is also very important result in group theory. So this theorem states that let G be an infinite cyclic group, then G must be isomorphic morphic to Z plus the group of all integers. That means if you have any infinite cyclic group, it is sufficient to study about Z plus. And the proof is almost similar. So let G is generated by A. Okay. How do I define a mapping from G to Z plus defined by phi of a to the power I, where it should go? Tell me where it should go.
Said I.
Very good. For all a to the power I belongs to G, because this is an element of Z. I is an element of Z, so it's not a problem. And in this way, you can show that here you need to show both injective and surjective, right? So now you can check that phi is injective, surjective, and homomorphism. The proofs are easy and quite similar. So I'm not going to prove this in details. Okay. So what you understand is that these total three groups are basically same with respect to the algebra. If you consider with respect to the algebraic structure, they are exactly the same. But if you look at separately, then they look quite different. So here the elements are like subset of a complex number, where they are the subsets, they are the elements of Z5, but the class 0 is not there. Here from class 0 to class 3, all the elements are there. That's why the important term in group theory is up to isomorphism, up to isomorphism, up to isomorphism. That means these three groups are same up to isomorphism, but individually they looks quite different, but their algebraic structures or algebraic properties are exactly identical. You cannot distinguish them. That's why they are said to be, they are equal up to isomorphism. So as a group, you can understand that this group and this group, they are not same, but algebraically they are very much same. That's why this term up to. So in many positions or many places in the book of algebra, you will find that up to isomorphism. So they are same up to isomorphism. Okay, very good. So we started with a group of order 4. Let's have a look at what are the all possible groups of order 4 up to isomorphism. So our next target is to find all groups of order 4 in bracket up to isomorphism. Now it is understand that if I have some classification, then we are done. We do not need to find infinitely many groups. All groups means it might have infinitely many groups are present. Already we have seen 5 groups. There may be plenty of other groups, but up to isomorphism is important. Okay, and this is now we will able to understand how algebraically we can start this and how we can algebraically write all the materials or all the things. The first one. So let G be a group. Let G be a group of order 4, right? Now, since this is a group of order 4, the elements of the group must divide the order of the group, right? Let A belongs to G such that order of A not equal to 1. That means A is not the identity element of G. Now, what could be the order of A? Then order of A could be how much?
The 2
Order
or
of A?
4.
2 or 4. If order of A equal to 4, then what can you say about G? Then
Cyclic.
G is
Cyclic.
cyclic. That means G is isomorphic to whom? Just now we have seen. G is
Z4.
Z4.
So a very big class of groups are gone by only one group. If there exists at least one element whose order is 4. Okay. So we assume that now we assume that G has no element of order 4. So if it has at least one element of order 4, then it is isomorphic to Z4. Now what is the negation of this? G has no element of order of 4. Okay. Let the elements be E, A, B, C. Now what is the order of E? is 1 and no element of order 4, then what could be the order of A, B, and C? Can anybody tell me?
2.
2.
So all the elements must divide the order of the group. So 2 is the divisor because there exists no element of order 4 and E is the only element. So only one case is there in which the order of every element is 2, right? Okay. Now A dot B. So by closure property, A dot B is one of the some elements, say A dot B equal to E, A dot B equal to A, E dot B equal to B, E dot B equal to C. That is the only possibility. By closure property, it will be one of them. So if A dot B equal to E, then what is your conclusion? Okay, let's first check if this one. If A dot B equal to A, that implies what it will imply?
B
B is
equals identity.
B equal to identity. That is not possible because B is another element which is not same as the identity, a contradiction. A contradiction. Okay, if this happens, that means if A dot B equal to B, then what will be your conclusion? A
So
equal
A
to
equals to
E.
E.
Again a contradiction. If AB equal to E, then what is the problem?
So B is the inverse of A.
A
Then B
equal to
is
B.
the inverse of A. But A is self inverse. But A is self inverse because order of A is 2. So what does it mean? A equal to B. Again a contradiction. So only case is remaining because it has to be one of them. That implies we must have A dot B equal to C. Okay. Similarly, you can prove that say B dot C equal to A and A dot C equal to B and the other way around. So now can you guess something? What group is actually it's giving to you?
The clients for group.
Exactly. Now it's basically gives you this table E, A, B, C. E, A, B, C. That is E, A, B, C, E, sorry, this is A, this is E, this is C, this is B, B, C, E, A, C, B, A, E. Exactly what we get. So similarly, you can prove the remaining. That means ultimately it gives you the idea that if it is not cyclic, then it must be there is only one possibility, and that possibility is it must be a clients 4 group, the K4 group. So if you look at this, then what would be your conclusion? See, all the properties here and there, they are exactly the same. You cannot distinguish any property. That means up to isomorphism, Z2 cross Z2 is same as K4. That means if you consider any group of order 4, either you will have Z4 or you will have K4. And most interestingly, both of them are commutative group. Okay, both of them are commutative group. Is it clear? So now you can understand that with respect to isomorphism, there exist only two groups of order 4. So let's try with some other classifications. Okay. So start with order of G equal to 1. How many groups are there up to isomorphism? How many groups are there up to isomorphism? Only one, right? E. Say order of G equal to 2. How many groups you can find?
1.
Sir, 1, 1.
Exactly 1
Sorry.
because Z2. Why only Z2? Because you can understand that if this is order 2, then any element, say A belongs to G, then if A not equal to E, then order of A must be how much? It must divide the order of the group. A must divide the order of the group, and this is a prime number. So either A is 1, order of A is 1, or order of A is 2. But since A not equal to E, so order of A can never be 1. That implies order of A equal to 2. And what that will imply? That will imply J, G is cyclic. G is cyclic. So isomorphic to Z2. Clear? If order of G is equal to 3, what will be your conclusion? How many groups?
Sir,
1.
1, 1.
1.
1. And that is Z3 plus. If order of G is 4, just now we have seen it has two cases, either Z4 plus or J4. If order of G is 5, then how many?
1.
1.
Only 1, Z5 plus. Now, very interesting, if this is 6, it can be proved by the argument that just now I have shown you for 4, that ultimately you will have exactly two groups, either this. So you can understand for any n, this kind of group will always present. Now some extra group may be there, and that is S3. So if you consider any group, for example, Z6, S3, D3, or M2, Z2. You remember, this is all collections of all A, B, C, D, such that date, if you consider A, this is date A not equal to 0, and A, B, C, D belongs to Z2. This order is also 6. This is also 6. This is also 6. So all of them, they look different, but up to isomorphism, they are same. Clear? Okay. But so do two types of, either this is commutative. If this is commutative, it must be cyclic. If this is non-commutative, it must be isomorphic to S3. So all the groups, they look different, but you can check on your own that their properties are exactly the same. Their algebraic properties are exactly the same. That's why they are cyclic group. Okay. So here also this is same as Z7 star. This is same as, so this is U7. This is same as seventh root of unity. All such Z belongs to C star such that Z to the power 7 equal to 1. So all of them, they are cyclic. So they are within one group, and they are, if this is non-commutative, then it must be isomorphic to S3. Now it's the concept clear what to mean by up to isomorphism. Clear? Okay. Okay. Now let us try to find few more interesting. So that way, if it is a P, say if order of G equal to P, a prime number, then G is isomorphic to ZP plus. This is clear now. If this is a prime number, then we have always a cyclic group. So that way you can classify many things, and that's why isomorphism plays an important role here. Okay, now I am going to give you a kind of big homework. So I'm writing few groups: Z plus, 3Z plus, 9Z plus, 101Z plus, S3, D3, say M2, Z3, R plus, r square plus r square means r cross r plus, okay, the same thing. Then maybe positive rational numbers with respect to dot, then zx polynomial ring with respect to plus, then S1, you remember S1, the circle group, then maybe say R quotient Z with respect to addition, maybe uh, C star, maybe C quotient Z plus. So C star is a group with respect to dot, right? Then all complex units root of unity. So that is all Z belongs to C star such that Z to the power n equal to 1, n equal to 1, 2, and so on. So all complex nth root of unity, okay? And maybe Q quotient Z, okay? So I have given you many groups, okay? I assure you that for every group, you will find at least another group as a pair. Of course, not the same one. For example, we have already seen that D3, S3, and M3, they are all isomorphic. So you can like make a connection between them. Okay. So please take a screenshot or write down the groups. Not all of them are very easy. What I'm saying, not all of them are very easy. You may not be able to do it now, but keep in your mind, in many competitive exams, you will find, or in many interviews, especially at ISI or during the NBHM exam or TIFR exam, the students are asked the question that can you tell me which of them they are isomorphic. For example, I say that these two groups are isomorphic. You need to prove. Okay. So each of them, so it's not very easy to prove that these two groups are isomorphic. Can anybody tell me any idea? So this is positive rational numbers and uh, this is Z plus. That means set of all polynomials with coefficient from X. Can anybody tell me what could be this idea to prove, how to prove that they are isomorphic? So please, there are plenty of others. In my problem set, you will find more even. But okay, for the time being, it's easy. But again, I am warning you that not all of them are very easy to solve, even at your master's level. But try to prove or try to see what with which group it will be isomorphic. You must use the concept of stack exchange. You might all have heard about the term stack exchange. If you type any question in Google, then you will find that most of the questions are being solved by one side known as stack exchange. So that's very powerful. You can use all those things. You have to use. So not all the questions can be solved by your own very quickly. But you may solve it. It may take some time, but sometimes it's good to have a look at the stack exchange problems. There we'll find lots of different types of proofs. Not all the proofs are correct. It give you some comments that, okay, these proofs are not correct. Here is some problem. So many eyes are there to see what you are doing or what you are checking. So that's why stack exchange is very important part of it. So please have a look at that and try to solve this problem. So all the groups. So here there are plenty of groups, and what I'm saying that for each group you will find at least one of them. For example, for this group you have 3 pairs, right? This one, and this one. Likewise, you need to find the pairing. Okay, so I will just give you a small hints how to prove this one. This one is quite innovative. So what I say is Zx plus is isomorphic to Q positive real numbers with respect to dot. First think about the idea that what is a positive real number. So it must be of this form a by b, and if a by b, if this is not 1, say a by b is not equal to 1, then must be some form. So whatever be the form, you can always write like a can be written as say p1 alpha 1 pk alpha k, and similarly b can also be written as say q1 alpha 1 qt, say not alpha 1, say beta 1 qt beta t. So that means it can be written as p1 alpha 1 pk alpha k into q1 beta 1 dot dot q, sorry, minus beta q t of beta t, right? Is this part clear to all of you? So it comes from the fundamental theorem of arithmetic. What it says, any number greater than 1, natural number of course, greater than 1 can be expressed uniquely up to some permutation of the prime numbers as a product of primes. So n can be written as p1 alpha 1 dot dot pk alpha k uniquely. For example, you can write say 72 as, how can you write in a product of 72? Tell me quickly. 2 is there, one of the factors. 3 is one of the factors. Anything else?
2 to the power 3 into 3 square.
2 to the power 3 into 3 square. So you can also write 3 square into 2 to the power 3. But their representation is same. That's why you say that unique up to the permutation of this primes. Okay. So if that is not 1, so in that case you can write say a may be 1, then only b is there, b is say greater than 1, then you can write b in terms of prime, and then in that case beta will be go up with minus of beta I. Okay. So any rational number, if that is not equal to 1, then you can always write in terms of this. Now I need to define a isomorphism from Zx to Q plus, positive rational number with respect to multiplication. Okay. Now, what is the identity element here? What is the identity element of Zx? What is the identity element of polynomial? Zero polynomial,
0 0.
That's 0.
and that must go to 1. That is the definition of the normal definition of the homomorphism, right? It has to be bijective as well as homomorphism. Now, any polynomial can be written as p1, sorry, any polynomial can be written as like this, a1 sorry, x plus ak xk. So any polynomial must be of this form where suitable, where a1 a2 ak belongs to z for some suitably chosen k, right? Now the question is, how will you define it in terms of a rational number, and that will give you a bijection. Any idea? Okay, I
এটা
will
আরেকবার
give.
বলবেন?
So what you need to do is you need to define a function phi from the set of all polynomials to q plus dot. That function should be a bijective as well as a homomorphism, right? Then only you will able to prove that they are isomorphic. Okay, I will give you a hints. So prime numbers are there, so you can enumerate primes because they are a part of natural numbers. So this is my first prime, this is my second prime, this is my third prime, and so on. Now tell me, how will you prove that this is a by? How will you define? So what you need to send here, From here, you need to send to some positive rational numbers. Okay. Now you understand that any positive rational numbers you can write in this way. And that too uniquely. So these are integers. So from here, which part is the integer? The coefficients. The coefficients are integers. Now, any guess?
Sir, P1 to the power A0, P2 to the power A1
Okay,
in this way.
let it, maybe we can, okay, P1 to the power A0, P2 to the power A1, P3 to the power A2. So let me write Pk minus 1 Pk, and then this will be my, okay, so it's less. So it will come till then Ak,
A2.
right? Yeah. Okay. So do you think that that will be a bijection and homomorphism as well? How will you prove that that is a bijection? So note that they are fixed primes, P1, P2, P3, P4. So they are the first kth primes, k
The
primes, k
last
minus
term
1.
will be pk to the power a k minus 1.
Okay. Yeah. So you're right. It starts from 0. So it should be ak. Sorry, can you please repeat? What should be? This is k. So this is, if it is k, then
pk
it
to
should
the
be
power a
k.
k minus 1.
K plus 1 to the power AK.
P Pk plus 1 to the power
To-
Ak, right?
Yes, sir.
Yes. Okay. Now tell me, is this a bijection? Is this a homomorphism? Is this an injective mapping? So that is your homework. And let me know in the next class that, okay, what is happening here. Done? Okay. So another problem. So this is quite interesting. So another problem could be find all homomorphisms. Find all homomorphisms between, I will also give you some hints. Find all homomorphisms from Q plus, say, okay, Q star dot to Z plus. Find all homomorphism, that means group homomorphisms from non-zero rational numbers to the set of all integers. Can anybody be start? Let pi be a such a homomorphism. Let pi be a homomorphism. Then phi of, you can understand that, what is the identity element here? Phi of 1 should be equal to how much?
0.
0.
Phi of 1 should be equal to,
0.
0.
phi of 1 should be equal to 0. Okay. Uh, yeah. Very good. Then what should be phi of minus 1? Can anybody tell me what should be phi of minus 1?
0.
Okay. Why? So phi of 1 equal to phi of minus 1 into minus 1. So this is a group homomorphism. That means phi of minus 1 plus phi of minus 1. So it's going to the additive group. That's why phi of AB equal to phi A plus phi B. And what is phi of 1? It is 0. That means 2 of phi of minus 1 equal to 0. And this is in integer. So addition of two integer becomes 0. What is the meaning of that? The same integer is 0. Then what is the meaning of that? What is should be the value of phi of minus 1 then?
0.
It has to be 0. So they are the first important observation that phi of 1 equal to 0 and phi of minus 1 equal to 0. Okay. The second observation could be, again, this is a non-zero rational number. Just my previous example, take any non-zero rational number which is, say, not equal to 1. Okay. Then A can be written as like this, a to the power A by B can be written as, say, the product of primes P1 alpha 1, Pk alpha k. So in my last example, it was positive rational number. That's why it was my only this. So this is positive power of some prime. So in case, what I'm saying, this is integer. That's why if it is in B, then B should be written as in terms of Q1, Q2, Qt. And then after that, you can write what I'm saying, that here ultimately this Q1, Q2, Qt, they are these primes, but ultimately the portion was above it, like minus beta of something. Okay. So instead of P1, P2 and Q1, Q2, I just write it in terms of just only P1, P2, Pk. But here, all of them, they could be integers, maybe negative, maybe positive. But note that this number could be negative as well. Then some negative will also come here. Okay. So suppose two cases. Suppose this is positive and then suppose this is negative. If this is negative, then some minus 1 will come here. Into some minus 1 will come here, right? So this term is positive and suppose this is negative, then you must multiply this with minus 1. So first assume that that is positive. Then you don't need to think about it. Now phi of A by B, how should I define phi of A by B? So it's same as phi of P1 alpha 1 dot Pk alpha k. Note that they are integers. In my previous example, the numerator was positive, or this one was greater than equal to 0. And since this one are negative, so that's why they are minus of this were there, because it came from here, 1 by. That's why I put minus. Now I made all of them together. So either this may be positive or this may be negative. That's why I put it 0. They all belongs to Z. So they are all belongs to Z. Now, how do I define a homomorphism from here to there? That's the point. So that it should be an element of Z. Okay. Now tell me one very simple thing. So that should be, by definition, this should be phi of P1 alpha 1 plus phi of P2 alpha 2 and so on. Phi of Pk alpha k. That is fine by definition of homomorphism. So they are product, and since the right hand side is an additive group, so it must be this. Now tell me any function from the set of natural numbers, say, okay, let say P be the set of all primes. Now give me any function, tell me phi, say not phi, say f is any function from P to Z. Can you give me any function? Any function from P to Z? Anybody? Any function. So f of some prime P, where it should go? Any function?
Sir, 2p.
2p. Very good. Take any function 2p. And let us try to define in this way. So this is, since this is phi, note that phi is a homomorphism. So that can be written as phi of, what should I write? Phi of p to the power alpha 1. Say p1 to the power alpha 1. This is phi of p1, how many times? Alpha 1 many times. Note that this alpha is an integer. If this is a positive integer, then I can write it alpha 1 many times. But if it is negative, then it should be minus alpha 1 times, right? So what you can write? You can write ultimately alpha 1 phi of p1. Clear? From the definition of homomorphism. So this is phi of p1 plus phi of p1 plus phi of p1 alpha 1 times. That's why alpha 1 phi of p1. If alpha 1 is negative, then it should be minus of alpha 1 times, and then the minus will come here, and then ultimately you will find the same thing. So here you can write it alpha 1 phi of p1 plus alpha 2 phi of p2 plus alpha k phi of pk. Clear? Now you give me this function. Wherever I will get, I will put 2 of, so phi of, so this is my any function, so I will apply this f here. So phi of p1 means 2 of p1. So 2 of alpha 1 p1 plus 2 of alpha 2 p2 plus 2 of alpha k pk. Okay. So this is my function. Now check whether this is a homomorphism or not. So how I have defined? I have defined phi of, so AB can be written in terms of this P1 alpha 1 PK alpha K, that is 2 of alpha 1 P1 plus 2 of alpha 2 P2 plus 2 of alpha K PK, alpha K PK. Now can you please tell me whether this is a homomorphism or not, group homomorphism or not? So here you have taken A by B, something C by D. Then C by D can be represented in terms of Q1, beta 1, QK, beta K. Okay. So beta T, not K, beta T maybe. And if you multiply them, A by B into C by D, then it will be divided like this. And then you will also have plus of 2 beta 1 Q1 plus 2 something, and then you can equate all of them. Ultimately, you will able to find that phi of A by B into C by D is same as phi of A by B plus phi of C by D. So this will be a homomorphism. Now can you, so you have taken any function here. So the function was according to your choice. I didn't talk about anything. So you gave me one function. Okay. Now somebody else may give any other function. Whatever be the function, you will always find this as a homomorphism. Whatever be the function, whatever be this value from the set of all primes to the set of all integers, you will always find this to be a homomorphism. So the last answer or the last question, if I ask you how many homomorphisms, then you can find. So how many homomorphism? How many such homomorphism? Anybody? How many such homomorphisms that you can find?
Sir, infinitely many.
Yes, but you might have started reading the cardinality of a set, right? So you know
Uncountable.
that, yes, uncountably many. So it is basically any function will do here. How many functions are there from set of all primes to the z? It basically the cardinality of this to the power of cardinality of this, not cardinality of this, 2 to the power of this. That means 2 to the power of cardinality of n, that is aleph naught, that is C, which is same as the cardinality of the real numbers. Okay. So if you think that the last part is not quite clear to you, it's okay. If you ask this question to maybe any master degree students, not everybody will able to answer this question. So you are at the undergraduate level 1, but still you have the capability to understand it very easily. That's why I teach you. So this is, so the number of homomorphisms from this set to this is basically the card number of such homomorphisms will be. So this is usually somebody's writes it like number of such homomorphisms is the order of R, which is C continuum. Okay. Don't worry if you don't understand it, but what I say that be optimistic because this kind of questions are very frequently asked in interviews. But the other way around, that is not very difficult to prove. How many functions are, how many group homomorphisms are there from here to this? That I am sure that you will able to prove. That part is easy, that you can do it very easily, but this part, if you are not quite comfortable with the logic that I gave to you, is perfectly fine, don't worry about it, but try to think how I did this. I tried to find a kind of basis concept. In vector space, you might have heard about the basis, which actually generates all the elements. So here also, by using the set of all primes, I can generate any positive rational number or any non-zero rational number. So I have just given you a kind of sketch how to prove this, but formally the negative, positive, alpha, beta, positive, negative, this case will arise that you have to write it properly. When you are going to write it properly, then only you will able to understand what is the basic idea behind that. But this part is quite easy. I request all of you to do this problem, and that requires basic properties of q star dot. That can be done easily. Is this clear to all of you? Is it fine? So if, do you have any question? If you have, so please let me know.